Okay, so here in this chapter we learned to do work. You need energy to do work. Yeah. And so we'll see where the world is getting its energy from. Okay. So today, roughly, this is still true. To run the world, this is the annual consumption of energy. 600 exajoules. So to run the world, the energy needed is 600 exajoules per year. And this diagram tells you where you're getting it from. Oil is that fraction, natural gas, coal. See, most of your energy, 500 exajoules, 80% is coming from what are called fossil fuels. These are organic matters that were converted to fuels millions of years ago. Okay. There's nuclear energy, hydroelectricity, okay, and renewables. These are all green energy sources. Okay. All right, let's put this in perspective. Like I said, a gigawatt plant, like a Hoover Dam, is a large power plant. It can roughly run 1 million homes. All right, so here's the total energy needed in a year. If you divide that by that, there's the year. Again, this divided by that time gives you the power requirement. That is how much energy is needed per second by the world. And if you divide that by gigawatt, a large power plant, that tells you how many power plants you need, how many Hoover dams you need to run the world. So to run the world, you need between 15 and 20,000 Hoover dams functioning at 100% all the time. That's what's needed. You saw that we're getting 80% of our energy from fossil fuel sources and 20% from renewables. Okay? That's where the energy is coming, and we are using that energy to do work. Okay? Now here's the deal. So this is natural gas methane, and the way you get energy is you burn it, meaning combine it with oxygen. The byproducts are carbon dioxide, water vapor, and heat. And this is what you were after. Okay. You use this heat to produce electricity, for instance. And about 30% of this heat can be converted to electricity. 35, let's say. What happens to the other 65%?
So lost to the environment?
Yeah, so you just dump it in the environment. So for every $3 of heat produced, you can put $1 to electricity and throw away $2. Imagine that. Do you do that every time you go to Publix or wherever, buy $100 worth of grocery and throw away $200 in the parking lot? Would you like that? All right, so here's the problem. This guy is the problem. So every time you burn fossil fuels, you're dumping CO2 in the atmosphere. And the more of this gas is in the atmosphere, the warmer the planet gets. Okay, so if there was parts per million, what does parts per million mean?
Number of those molecules per million sampled in the air.
Per million atmospheric molecules. So what are the atmospheric molecules? Oxygen and nitrogen. Nitrogen is 71%. So for every million of those molecules, if you had 0 carbon dioxide molecules, the temperature of the planet would be minus 18 degrees Celsius, the average temperature. That's too cold, we don't want that. So if you were on the planet, let's say 300 years ago, okay, 250 years ago, you had 280 parts per million of carbon dioxide in the atmosphere. The average temperature is 14 degrees Celsius. This is good. We like this. In the last 50 years so on, we've been dumping a lot of CO2 in the atmosphere. It's 420 parts per million. Okay. The average temperature is about 15.3 degrees Celsius. This is global warming. Right. What happens if this temperature gets to be 16 degrees Celsius?
Lose Antarctica?
So all of Greenland ice will melt? Now, the calculation is hard, but it might melt in the next 500 years, 1,000 years, whatnot. And sea levels would rise by about 7 meters, twice the height of this room. It would displace about 10% of the world's population. All right, if I ask you to move out and go make a life in another city, is that easy to do? All right. Asking that of 10% of the world's population. All right, so that's the problem. So this is one of the biggest problems facing mankind. Okay, so use of fossil fuels is you're dumping carbon dioxide in the atmosphere and global warming. Well, is there a way out? Is there a solution? Let's say in the infinite future. Well, not in the infinite future. Okay. In the very immediate. Yeah, okay. So, to run the world, we said about 16,000 gigawatts is needed. That's 1,000 times 10 to the 9, that's 10 to the 12. So 16 terawatts is needed. Okay, so 16 times 10 to the 12 watts is needed to run the world. Okay. 16,000 Hoover dams. Okay. So world energy consumption 16 terawatts. There's that much sunlight falling on the earth. 23,000 terawatts. You just need to harness one part in 1,000 of the sunlight falling to run the world entirely on sunlight. There's plenty of wind energy available. You can run the planet on just solar and wind. And right now, these are the two cheapest sources of energy. Yeah. So there is hope for you guys. All right. So here's the deal. So here's our atmosphere. You get energy from the sun, and it comes in the form of visible light. And, if you're getting energy continuously, you're getting energy. And if you don't re-emit this back, then you'll just warm up. You keep warming up. So whatever you're getting, you have to radiate as much energy to maintain your temperature. So what you're getting is visible light, and what you're radiating is infrared light. And that's a function of the temperature of the object. This guy is 6,000 degree Kelvin. It's emitting visible light. We are about 300 degree Kelvin, and we're emitting infrared light. So if the amount you're emitting is not equal to what's coming in, your temperature would rise. If this was less than what's coming in, your temperature would rise. If this was more than what's coming in, you would get colder. And if this is equal to what was coming in, your temperature will remain steady. And that was true till the 1700s. Your temperature was steady. What you were emitting was equal to what was coming in. In the last 50 years, this has decreased. It's less than what's coming in. And you're warming up. And the reason you're emitting less is because we are changing the nature of our atmosphere. And as you dump carbon dioxide blocks this radiation from going up. The greenhouse gases block the radiation from going up. And that's the problem. All right, so this is the radiation coming in, okay? The atmosphere is essentially transparent to this radiation, these wavelengths, and what we're emitting is this. And as more greenhouse gases get in the atmosphere, less of this radiation gets to space. Okay, so there's a CO2 molecule, and H2O is also a greenhouse gas, but that's a secondary gas. Okay, you emit infrared radiation, carbon dioxide absorbs it, and re-radiates it in all directions. So half of it is radiated back. Yeah. You get trapped. So without any carbon dioxide, the temperature would be minus 18 degrees. At 280 parts per million, which was the pre-industrial revolution levels, temperature was 14 degrees Celsius. And now it's about 15.3, and your goal is to remain below 16 degrees. At one time, we were talking about 10 years ago, maybe 15.5, but we've abandoned that goal, I think. See, if there was no greenhouse gases, this is what would get to space, but because of the CO2 present, see, all this is being reabsorbed. %90 of the heat trapped is going into the oceans. Yeah. Okay, because of the greenhouse gases, remember I said what is coming in is greater than what is going out. Well, how much greater is that? Okay, 3.22 watts per meter square. For every meter square of the earth, this is a meter square. There's 3.22 watts, joules per second, more coming in than going out. Well, that number doesn't, so we'll put that in perspective. That's 1.6 times 10 to the 12 watts. Remember, to run the world, you need this many watts, 16 terawatts. This is 16,000 terawatts. It's 100 times more energy than is needed to run the world. Okay, 100 times more power. This is equivalent to exploding 20 atom bombs every second, 24/7, and trapping the heat. This is massive. Okay, so here is the CO2 levels over the past 10,000 years. It's shot up since the Industrial Revolution. So currently we're about 430 ppm. You can look it up. There's CO2 meters on the web. We're burning fossil fuels and dumping about 10 gigatons of carbon dioxide each year. We have dumped about 500 gigatons of carbon in the atmosphere, gigatons of carbon in the atmosphere. Okay. That's about 50 years worth at the current rate. So simulations suggest that we can dump another 500 gigatons, but yes, you don't want to take that risk. Okay. So if the temperature rises to 16 degrees, the irreversible loss of Greenland ice sheet is triggered. Okay. So the associated sea level rise could be 6 meters or higher. Yeah. About 10% of the world's population, 700 million people, would be affected. Yeah. Okay, again, you can run the world entirely on just wind and solar. Okay, so puts things in perspective. If you covered those black dots with solar panels, you could run the entire world. Okay. These would be 6 300 kilometers by 300 kilometer arrays. 300 kilometers is 200 miles by 200 miles. Okay, so here's, yeah. This is one of those arrays. This is Florida, by the way. Okay. Don't laugh at my Florida. All right, so this is 2012, but this is a Stanford University produced graph. This is essentially, okay, back in 10 years ago, 15 years ago, this was all of our energy was coming from fossil fuels. Okay. In 2050, another 25 years, let's say we could run the world on just renewables. If we keep the current mix, you would need 20 terawatts, 20,000 Hoover dams if you kept the current mix, this mix of fossil fuels. But if you switched over to renewables, all you need is 11,000 Hoover dams instead of 20,000 Hoover dams. Why is that?
Because renewables typically more efficient.
The processing.
So when you remember when fossil fuels, you're burning them and only about 30% of the heat is utilized. But if you're with renewables, you're producing electricity, and machines running on electricity are 90% efficient. So your electric car is 90% efficient, where your gas fuel car is 20% efficient. Yeah. So you would need less, and it would be clean energy. Okay. So my generation sort of created this problem, but it's for your generation to fix it.